Okay, good afternoon, everyone. My name is Yi Zhuang. I'm from Yanmin Jiaotong University. And today's student, we have Professor Chen from NTU and Professor Liu from National Taiwan Tech. Yeah, Taiwan Technology. Yeah, and Professor Hong from NTNU, Professor Lin from Fujian University. And this afternoon session, we will have 3 teams. Okay, and the first team is J ammeter. The second team is WO niter. And the third team is N accelerometer. Okay, so it's each team captain to introduce your team member briefly. Starting from here, opponent.
Hi, we're Team On Iron from Typt American School. I'm Justin. This is Junie. This is Alex. This is Charlene, and this is Yin Ho.
Good afternoon. I'm Captain Huang Ray from Team Excelsior. We're from Concordia Middle School. These are my teammates: Chen Yitai, Zhuang Yufei, Li Kunxian, and Lan Shaochen.
Hello everyone, we are Team Amanda. I'm Zhongchen. This is Wu Xiaoqi, Chen Si, Zhao Jie, and Ye Zhiqi.
Okay, good. So let's start today's this afternoon session. And the opponent will challenge the reporter for the problem. 好，自选的。好 ，OK。来看看题目。OK。OK。So reporter will choose the problem number 1 and please write down the report presenter and also the 3 team presenter on the record. Okay, the reporter has 5 minutes of preparation. Okay, then before to take the floor.
Okay, hello everyone, my name is Typt from Typt, and the topic of my report today is problem 1, fractal fingers. And here is the problem statement. The effect of fractal fingering can be observed if a droplet of an alcohol mixture is deposited onto diluted acrylic paint, and how the geometry and dynamics of the fingers influence the relevant parameters. And we're focused on the size variation of the fractal fingers and the relationship between evaporation and the droplet fractal. And here is the experiment video. We use isopropyl alcohol plus pigment cut into the diluted acrylic paint. And the isopropyl alcohol, also called IPA. And we can see the IPA will start to expanding and split into the fractal fingers. And first we observe the process of the expanding. Because of the gravity, the droplet will be flattened, and because of the height of the droplet is shorter, so the potential energy will decrease. And the surface area becomes bigger, so the surface energy will increase. And because it is flowing, so the kinetic energy will increase. And because of the evaporation and chemical reaction, it will absorb the heat, so the energy of the expanding will decrease. And here is the segmental instability. When the less viscous fluid inject, replacing the more viscous fluid, and it will form the finger. And here is the theory about the diffusion. We mix the isopropyl alcohol and the diluted acrylic paint and leave for a long time, and we see they have no delamination, and so they are visible and prove that IPA will diffuse in the diluted acrylic paint. And here is the theory about why it will have the fragment, and it's the curvature. Because of the evaporate, the liquid, it will have the disturbance, and so it will affect the curvature and the pressure become different. So it will form the finger. And here is the theory about the dimension. The fractal is between one-dimensional and two-dimensional. And one-dimensional is a line, two-dimensional is a plane. And we use the box counting dimension to calculate the dimension of the fractal fingers. First, we cut the fractal fingers picture to many tiny squares. And the NB is the number of the fractal fingers occupied, and the S is the tiniest square's side length. And here, we take a log of this, and we can get log NB equal to log K plus dB times log 1 over S. And when the S is very small and almost equal to 0, the log K can ignore. So we can get the log NB equal to dB times log 1 over S. And we calculate the dimension, and it's about 1.67355. And here is the Young's equation. The green arrow is gamma 1, surface tension of acrylic paint to air. And the blue arrow is gamma 2, surface tension of alcohol to air. And the orange arrow is gamma 3, surface tension of alcohol to acrylic paint. And when gamma 1 is more than gamma 2 plus gamma 3, and it will keep expanding. And when the gamma 1 is equal to gamma 2 plus gamma 3, it will stop expanding. And here is the Marangoni effect. Because of the IPA is very easy to evaporate, and the evaporation is occur from the surface, and the edge it have the side and top surface, so it will evaporate faster than the center, because the center just only have the top surface. And so the edge proportion of the water is higher than the center proportion of the water, and the water's surface tension is bigger than the isopropyl alcohol surface tension. So the edge surface tension will higher than the center surface tension. And the Marangoni effect said the fluid with high surface tension, it will pull out the fluid with low surface tension. So the isopropyl alcohol, it will flow from center to edge. And the surface tension gradient, it will cause the Marangoni pressure, and the surface tension gradient increase, and the Marangoni pressure, it will also increase. And the droplet expanding velocity will become faster. And here is we do the saturated vapor pressure experiment to prove the Marangoni effect does exist. And we do this experiment in we do this experiment in the acrylic box and spray isopropyl alcohol in it and let the environment is the saturated vapor pressure. And we can see when that it didn't have to evaporate, it will hidden from the fragment. Okay, and so the segmental stability set only set when the less viscous fluid inject replace the more viscous fluid and it will from the fragment. But we do a saturated vapor pressure and we can see if the experiment didn't have the evaporate and it will hidden from the finger. And this is the rectal fingers picture. It has this inner circle radius, and this is the segmental instability picture, and it didn't have this inner circle. And the segmental instability is experimenting in two boards, and we don't have two boards. So we think this segmental instability is not the theory about these rectal fingers. And here is the theory about pressure. The Fm is the membrane force, and because of the evaporate, it will decrease by time. And the membrane force, it will cause the IPA expanding. And the Fv is the viscous force, it will block the IPA expanding. And here is the theory, and this part is, the first one is membrane effect velocity, and the second is expand time, and the third is conservation of evaporation. And the fourth is the conservation of volume of water. And transposition of these four formula, and we can get the expanding time formula and the inner circle radius formula. And here is the experiment setup here, and we use pipette and isopropyl alcohol plus pigment in the pipette, and diluted acrylic paint in the petri dish. And we change the viscosity of diluted acrylic paint and isopropyl alcohol concentration. Here is our definition about this experiment. The blue line is the outer circle radius, and the yellow line is the inner circle radius. And the outer circle radius minus inner circle radius equal to finger's length, and the red line is finger's length. And the right picture, we define this yellow line is the white of the finger. And first, we change the viscosity of diluted acrylic paint and control the IPA mass percent and its 20 microliter and the temperature. And you can see when the diluted acrylic paint with low viscosity, and the finger will become wider. And here we'll discuss about the radius, and we can see these two pictures is that the viscosity content is it will affect the expanding time and the inner circle radius and the diffusion coefficient. And we can see when the viscous force decrease and the expanding velocity will increase and the expanding time will decrease and the radius will increase. And here is the discussion about the fingers. The left picture is the outer circle radius, and the right picture is the finger's length over time. And you can know the viscous force decrease and the expanding velocity will increase and the expanding time will decrease and the outer circle radius will increase and the finger's length will be the same. And here is the discussion about the viscosity of diluted acrylic paint. And this chart is the white of the finger when the viscous force increase and the white of the finger it will decrease because this is the viscous force and it will squeeze from the side to let the fingers become narrow. So this chart, the y-axis is the white. So we can see that it's decreased. And this one, y-axis is the dimension. And we can see when the viscous force is increased and the dimension of the fingers also increase. And next we control and we change the concentration of the IPA mixture, and we can see when the isopropyl alcohol becomes 32.5% and it will start to from the finger. So we call it 32.5% is the critical concentration. And here we didn't change the acrylic paint viscosity, so the finger's wide remain the same. And it will expanding to, and when the IPA with high concentration, it will expanding to bigger area. And here, because of the low concentration, it needs more time to evaporate, so the surface tension gradient, it will increase, and the expanding velocity also increase, and the inner circle radius increase. And expanding time also increase. And we take a look of the inner circle radius and the time, and we can see the inner circle radius is approximately equal to the power of 0.25, and this inner circle radius formula is the power of 1/4, and 1/4 is equal to 0.25. And here is the log time, and we can know that it's approximately is the 0.5, the power of 0.5, and here the time formula is the power of 1/2. So we think that the formula is very stick to our experimental data. And here is the, we can see when the surface tension gradient increase and the velocity also increase, and the outer circle radius also increase, and the times increase, and the finger length also increase. And here is when the viscous force is the same and the fingers wide also the same, and the dimension of the fractal fingers also the same. And here's the conclusion. Gravity effect cause the expansion, viscous force cause the fractal fingers, and have different wide, cause the fractal fingers have different wide, and the curvature cause the drop dead fractal. And viscosity of the liquid can increase, wide of the fingers will decrease, and the expanding velocity will decrease, and the expanding time increase, and the fingers length will be the same, and dimension decrease. And concentration of the IPA increase, the wide and the dimension of the fingers will be the same, and expanding velocity increase. And expanding time also increase, and the radius increase, and the fingers length increase. And thank you for your attention.
Okay, thank you. The opponent asked question. Moving.
Okay, thank you, reporter, for your report. And I would like to ask, did you consider the impact of an angle where the disc is placed in?
Pardon?
Did you consider the angle in which the plate that you used was placed on?
The
was
plate.
it slanted or?
Control angle.
Yeah.
Yeah.
Did you quantify the velocity that would reach the surface?
What velocity? Expanding velocity.
Yeah.
It will.
The velocity of the drop.
The velocity of the drop.
Yeah.
Oh,
Was it the same or no?
it's the same or no?
Okay, I'll move on. Did you keep the height of the drop the same?
Huh?
Did you keep the height?
Oh yeah.
How tall?
It's we keep the height is the 0.5
For
centimeter.
curve for your theory, did you fit your data into the curves? Did you fit your data into the theory curve?
Oh, we didn't do that.
So did you change the type of alcohol to different types of formula?
Different type of alcohol. Oh, we didn't change the different type of the
Did you change the parameters such as temperature,
temperature. Oh, we control the temperature.
but you didn't change it?
Yeah.
Have you looked into the formula that's called Healy-Shaw flow?
No.
How did you did you quantify the number of fingers?
The number of the fingers.
Yeah.
Oh, we do that, but the number of the finger is very.
Yeah.
Everyone
Yes or
counts
no?
that is. Oh, okay. Yes.
Did you explain the randomness of the motion?
Oh,
Random. How random it is.
random of this one.
Yeah.
Oh, yes.
Okay, that's it for the question. Thank you.
Okay. The presentation for the opponent, 3 minutes. hand.
So,
Want to take the floor?
good afternoon, everyone. My name is Junie, and I'm all-nighters. I'll be opposing fractal fingers. So the problem statement reads, the effect of fractal fingering can be observed if a droplet of an ink alcohol mixture is deposited onto diluted acrylic paint. How are the geometry and dynamics of the fingers influenced by relevant parameters? And so main focus of our opposition is going to be viscosity, dendritic pattern, and depth. So the overview of the observation was the reporter had clear phenomena demonstration, identified the dendritic pattern. However, they did not address the cause of randomness that causes the fractal fingers. And they had appropriate methods for counting the number of fingers. However, they did not have any reference points such as the drop location with respect to the perimeter, whether it was different or same every time. And then they assumed same volume of drop. And also, they didn't think of the created dip, which changes the velocity. Their theory, they provide qualitative overview, however, did not employ the equations from the Healy-Shaw's law, and they implemented Stokes' equation for diffusion. However, there was little quantitative theory. They also implemented qualitative concepts from Marangoni effect and proposed theory for fractal dimension, but there was no radial motion considered, as well as no function of randomness, and the drop height was not addressed. And there was no rigorous definition of width of the finger, which looks very ambiguous in the image. And the experiments, the good thing they did was they tested some parameters, so the paint viscosity and IPA concentration was tested. However, it was not clearly shown whether in the experimental setup there was unclear drop volume, and they did not account for paint drying during the spread, and they did not investigate the velocity of the paint, and they didn't have important test parameters such as the temperature, drop height, and the drop volume. So the data analysis, they had some error bars, however, there were no error bars for many graphs, and other error bars had overlap oftentimes. They had some proportional relationships suggested as viscosity, IPA concentration, which leads to the finger length. However, they did not have any implementation of theory curve fitting, and there was only the best fit. And you had analysis on error caused by inconsistent amounts of solution drops. So our discussion points are going to be, for the theory, we'll talk about viscosity formula in relation to speed, Healy-Shaw law, and the diffusion limited aggregation. And the experiments, we're going to talk about impact of various concentration and dilution factor, and velocity of the growing fingers, and the optimal ratio of paint and ink solution where you can spread the fastest, and the slant of the plate of the initial angle. So our data analysis will include the randomness, gap spacing, and explanation of time evolution, and spontaneous fingers at molecular level. And then also talk about basic geometry in relation to final pattern. Thank you. We'll move on to discussion now.
Okay. Discussion with the reporter.
Could you go to the problem statement slide? Okay, so I want to bring up the question again of whether you quantified the numbers of fingers, or you measured or tracked the number of fingers at different times or not.
You say the number of the finger.
Yes.
I think the number of the finger is not the regular. It will be the number of the finger. We count that, and everyone count that is not the same. So
Okay.
I think that.
So you say there's a random motion of number of fingers, right?
Yeah.
And then it says the problem statement clearly suggests that you need to investigate the geometry and dynamics, which means that number of fingers impact the geometry and dynamics of each fingers, which will change the number of fingers, right?
Mm.
Yeah.
Yeah.
So I think you should include the number of fingers. So as a function of time, you can have numbers of fingers. Can I use the word?
Yeah.
If you include the number of fingers as a function of time, you can also see that the number of fingers is obviously going to grow in some pattern, but your model doesn't include, and it only talks about the geometry.
Your finger is you count. This one is one finger, or this one is 3 fingers.
And every single small finger.
Small fingers.
Yes.
Okay. And how do you define the finger that maybe it's that is very small, and you think it is a finger or not?
It is a finger.
It is a finger.
So I would say what you can do here is you can use the noise function, because you agree that the number of fingers or the geometry can be random at any moment, right?
Yeah.
So you would have to make a function in computer program or something that suggests that your number of fingers are gonna depend on the amplitude and then some random number multiplied by the amplitude. So that when you calculate the number of fingers, it's gonna have a random motion of somewhere in between, again, 0 to 1. And then this way you can find the number of function and then number of noise function, and then this will help you find the simulation for how the fingers spread,
Okay.
right? Okay. So there was also during the problem with the plate,
Yeah.
when the fingers spread to the side, right?
Yeah.
There's going to be a dry, not only the evaporation, but also the dry of the alcohol you dropped, and also the dry,
Dry.
becoming drier, no water.
No water?
Like water evaporates and then it's going to be drier, like
Oh,
the
yeah.
paint and the drop as well. So how did you account for this?
Can you repeat your
So
question?
when it spreads to the side, right? The paint is going to dry. It's going to
Yeah.
lose amounts of water. So how did you account for this in your
Oh, I
model?
think that is not very not more effect to this.
Okay, well, however, if you think about, your presentation talked about the diffusion rate. However, when the paint dries, the diffusion rate is going to slow down. So it is going to impact the
Oh, I think because the
velocity.
isopropyl alcohol it will diffuse in the diluted precipitate, and the diffuse it will let the IPA expand faster.
So you can say it's qualitatively, but however, you cannot quantify by how much it's going to get faster, right?
Yeah.
Okay. Also, what do you think about considering the relevant parameters such as temperature? You didn't talk about temperature in your presentation. However, yeah.
Well, I think the temperature it will affect the evaporation rate and cause it affects the surface tension. And we control it. Actually, we control the temperature. And here is the pipette and here is the petri dish.
Yes.
And here we have a heating plate.
Okay. So why don't you try at different temperatures to see how much the diffusion rate changes, or how many fingers, or just how far the velocity can go.
We just want to control it.
Okay. Also, since you draw the diagram, you can see that the height, how did you control the height is always the same?
Oh, we use the ruler here, and here is 0.5 centimeter,
Okay.
and we drop.
So you only use the ruler, and then pipette is going to be held by your hand,
Yeah.
right? So when you release the pipette, there's going to be a small amount of initial velocity where you drop, because your hand is not very, as you know, like,
So you think it?
it's going to change the motion, of course.
Oh, okay.
So if you can make a setup so that the pipette is fixed, and then if you drop the alcohol, it's going to be better.
Okay.
Also, you said you didn't account for different chemical formulas of alcohol.
What?
Did you use any different types of alcohol?
No.
What do you think is the impact of using different types of alcohol?
Because of the isopropyl alcohol is a type of the alcohol, and we think that is not the main variable we need to do that.
So could you go to the slide where you had like a diagram of like the, okay, we can do that one.
Okay.
Yeah, this one. So depending on the formula of the alcohol, the spread or the surface area is going to change, right? At a
Yeah.
molecular level.
What?
At a molecular level, very small, if you look into very small collision of the water molecule, for example, the formula of the alcohol is going to impact how much it spreads for time, right?
Yeah.
Yes. So I think also including the different formulas or different types of alcohol is going to impact your results as a parameter. So another parameter you can consider. Also, did you calculate the diffusion coefficient?
We have that is the diffusion coefficient formula.
Okay. So did you have like a quantitative value for it?
Yeah.
And then how did you use it to explain the radius increase or the velocity of the radius?
Oh, we think that diffusion it will affect the isopropyl alcohol expanding, but it will not affect more the it will not more affect the result.
So
It's a
by,
little bit,
okay, so a little bit. So can you quantify how much you mean by a little bit?
a little, it just will get the IPA extending faster.
Okay. So no quantitative comparison, right?
Yeah,
Okay. Could you go to the slide where you talked about critical concentration?
critical concentration.
Yes. I saw that you said the critical concentration was 32.5%.
Yeah.
Right? So could you explain how you determine the value of 32.5% and then,
This
yeah, how did you determine 32.5%?
32.5%, because that here is starting from the finger, so that is the critical concentration.
Yes. So how did you exactly get the number?
Get enough, do the experiment, and we can know.
Can you write out the formula or any sample calculation
No.
that you used for it?
We didn't have the, we just do experiment and know that 32.5% is the critical concentration, and
Okay, so I think you need to be more clear about like what you define as critical concentration.
the critical concentration, and when it starts to from the finger,
Yes.
and we define that concentration is the critical concentration.
But if you just give a number like 32.5%, I'm not sure what you're talking about or what equation you got it from, right? So, can I also talk about the Marangoni effect? So can you explain why when you have low surface tension in the middle and it's going to move toward the high surface tension in a molecular level, can you draw the diagram?
This is the isopropyl droplet, and this is the H,
Okay, only the surface tension.
only the surface tension.
Yes.
Surface tension here is the acrylic pant to air surface tension, and here is the isopropyl alcohol and the air surface tension of unit.
So how does the surface tension, how does it go from low to high surface tension?
Low to high surface tension.
Yes, that's because that's what the Marangoni effect suggests, right?
The Marangoni, our surface tension is here, because here is evaporate faster than here.
Okay.
And the water surface tension is bigger than the isopropyl alcohol.
Yes.
And
Well, that's just stating what the Marangoni effect is. Like, I just want to know how you want to explain the low surface tension to high surface tension.
yeah, it's
Okay.
and because here is evaporate faster than the center, so the proportion of water here
Yep.
is lower, and yeah, it is higher, and here is lower.
Okay. I think
And-
we can move on now. That's enough.
Um,
Okay. Yeah.
And
So. Yeah.
water surface tension is bigger than isopropyl, and here proportion of water is more, so here surface tension is more.
Okay.
And the Marangoni effect is
Okay.
the
Yeah. That's
surface
good. That's
tension.
good. So, what's the effect of the size of the container? Do you think there's an effect of differing the size of the container because that parameter was not included?
Okay, and you say,
Yeah.
okay, and
It's going to impact how much you move and the final velocity as well.
we use the same size
So
of
that was not a parameter, right?
yeah.
Okay, finish? Okay, opponent has 1 minute to summarize the discussion.
So to summarize our discussion, the reporter's presentation talked about the number of fingers, and we also talked about random motion of fingers, which is essential to the problem statements, but they didn't have a graph such as how does the number of fingers impact the geometry. And also, they can express the noise function as a function of time using programming randomness, so they can make a simulation to show that there's a randomness when the fingers spread. And there's also paint drying that they didn't consider, and it cannot be quantitatively explained by the reporter. And however, this slows down the diffusion rate, which needs to be addressed. And there was also one parameter that was not considered, that's temperature of surrounding, which influences the evaporation. And this has to be included in parameter test. So also, it was also handheld, the dropping of the pipettes. There's different types of alcohol they didn't address. And the diffusion equation based on the equation is inaccurate. and the critical temperature was kind of suspicious, 35.
Right hand job. The reviewer asked question.
Okay, so for the reporter, and the opponent, both of you agree that Maragoni flow is the main reason that spreads the mixture out. Do you agree with that?
Yes.
And do you agree with that? So for the reporter, how did you measure the radius of the length, the radius of the finger? And how did you define the fingers?
Oh, define the fingers.
Yes.
Fingers length is outer circle radius minus inner circle.
Okay, so for page 21.
Page 21.
So how did you measure these kinds of fingers inside your experiment? Like these kinds of fingers that it's randomly formed, but I cannot see how you measure these kind of fingers. For example, the 32.5%, like which finger are you taking to measure?
To measure. We just measured it 50 to 100%, and we don't measure it 32 point.
So you're not able to quantify like when the percentage is too small, you're not able to quantify the fingers.
Yeah.
Okay. So why is the main reason that causes the Maragoni flow to decline by time?
To decline.
By time, or do you think that the Maragoni flow will not change by time?
Because of the evaporating will absorb the energy.
Okay. Do you agree with that?
Yes.
So it's the Maragoni flow to decline by time that causes the spreading motion to stop. Am I correct?
Yes.
And for the reporter, the finger motion is randomly formed but not symmetrically. Am I correct?
Yes.
And so why do you think causes this result?
Because of the glue is unstable and yeah, it's like that.
And why do you think causes the finger to be formed randomly?
It has to do with the randomness, or it can be addressed in the noise function.
I mean, like, why is it random?
It's going to happen, and you're going to have to look at molecular level.
Okay. So do you think that it's because the surfactant is unevenly mixed, or do you think that there are other reasons about the randomness of the fingers?
There can be other reasons.
Okay. For the opponent, do you think that the initial capillary wave will affect the fluctuate of the motion?
Yes.
So for the reporter, do you think that this unique shape is formed because the mixture wants to remain its minimum surface energy?
What?
This unique finger shape is formed because it wants to remain its minimum surface energy, like the
Can you
finger.
explain cleaner?
So do you think that the finger is formed because the mixture wants to remain its minimum surface energy?
Surface energy.
So do you think that it's because it wants to remain its minimum surface energy?
I don't understand the question.
Okay, time is up. The viewer has 2 minutes of information. Okay, reviewer, take the floor.
Honorable jurors, fellow competitors. This is a review from Team Excel here, reviewing problem number 1, fractal fingers. Problem statement. The effect of fractal fingers can be observed if a droplet of the ink alcohol mixture is deposited onto a diluted acrylic paint. How are the geometry and dynamics of the fingers influenced by relevant parameters? Due to your problem statement, I believe that we should focus on the formation of fingers and how the geometry and dynamics of the fingers influence the relevant parameters. This is a review of the report. For her experiment part, she conducted parameters including the inhibition of Marconian effect to prove that Marconian effect does exist in her experiment, and also the concentration of IPA mixture. And she talked about the theory regarding Marconian flow, Stefan-Taylor instability and diffusion, and Young's equation. And she did data analysis for the radius of droplet and the size of the droplet. And these are the pros and cons that I think your reporter had. First of all, she had a clear observational video about the spreading of Marconian flow. And she did a phenomenological explanation about how Marconian flow is caused. However, there's too much introduction for the theory part, which causes she did not discuss too much about her experiment result. And there's no direct connection between the theory and her experiment data. And she controlled the temperature of the Petri dish from a heating plate for the initial condition. And she well defined about finger in the inner outer part of the rim. However, she did not define the concentration and volume of the liquid well, which I believe might affect the dropping of the, and affect the fluctuation of the spreading. And for the review of the opponent, he noticed that the lack of quantifying the finger that the report did not mention, and he discussed about the random motion of the finger. However, he did not focus on the physics inside behind the phenomena, how Marconian flow is stretched and decline after time. And he did not discuss it on experiment result too much. And he gave own opinions about how the initial condition of the droplet might cause a fluctuation of the Marconian flow. And for the first key discussion about the qualitative explanation, the opponent asked, what is the main reason that causes the phenomenon to happen? And the reporter said, it's Marconian flow to spread it out. I partially agree with the reporter. I believe it's a concentration gradient that causes the surface tension gradient different and causes the Marconian flow inside the system to spread out the mixture. And after that, the mixture tries to remain its minimum surface energy that causes the unique finger. And for the next discussion about randomly formed fingers, the reporter said it's unpredictable. I believe that it's because the initial condition of the dropping from the syringe might cause impact on the randomness, including the dropping height and the dropping volume that causes a fluctuation for the mixture. And our question, why will the spreading motion eventually stop? The reporter said it's a Marconian decline by time, and the opponent agrees with the reporter. In this part, I believe that it's because when Marconian flow spreads out the mixture, the center part of the mixture has higher concentration, and after the time it causes, after it evaporates, it causes the Marconian flow to decline by time, and it reaches balance with the viscosity for it to shrink inside and stops the motion from spreading. And these are points missed. First of all, the formation of the finger. I believe that reporters should talk about more about the geometrical characteristics and also the dynamics of the fingers, since the problem statement has asked for these parts. And geometrical, I believe that they can discuss about the amount of the fingers formed, and for the dynamics, I believe that she can discuss about how the spreadings of the fingers, for example, the spreading speed and how many spreadings are there. And the effect of surfactant might be the reason why it will not shrink into small droplets. I believe that they could discuss about the initial disturbance causing by dropping height. Thank you.
The reporter make the concluding remarks.
First, I want to thank the opponent and the reviewer. And the experiment will drop the IPA into the diluted acrylic pan, and it will start to expand and split into fractal fingers. And we do the saturated vapor pressure to gauge for the segmental instability, and the Marconian effect causes the expansion, viscous force causes the fractal fingers have different width, and the curvature causes the droplet fractal. And we change the viscosity of diluted acrylic pan and the concentration of the IPA, and discuss about the width, radius, and fingers length and the dimension. And the dynamic, we talk about the dimension. We talk about the expanding time and expanding velocity, and the geometry. We talk about the width and the radius and the length. So we have discussed about this too, and we think the number of the finger is very random, and everyone calculate the numbers are different very much. And as for the opponent question, we put the critical concentration question, we put the alcohol slowly until the 32.5%. Like we let it 31% and 32% and 32.5%, and do the experiment to know the critical concentration. And it has the finger, so we define that is the critical concentration. And so we don't use any formula to get 32.5%. We just do the experiment. And as for the reviewer, we think the theory is important, so we explain more about, and our data is connected to the Meringen effect. Okay, and thank you for your attention.
Okay, thank you. Now the time for a question from Julie. Question?
Question for the researcher. Could you comment on your definition of the width, finger length, and the dimension? Do you think there's a correlation between these three parameters?
Can you?
Your finger width, your finger length, and your dimension of your fingers. Could you comment on the relationship of these three parameters?
When the viscosity of diluted acrylic paint, it will let the width of the finger become narrow, and when the concentration of the IPA become higher, and the radius and the finger length will also increase, and the dimension when we change the viscosity of diluted acrylic paint, and when the viscous force increase and the dimension it will increase.
Any other questions? No? Okay, then I will have a question. So in your experiment, what do you think is the most important factor? Because both of the opponent and the reviewer mentioned about the surfactant effect.
Most important factor is the evaporation. Because of the evaporation, it will affect the surface tension gradient, and it's related to the Meringen effect.
Okay, and how do you think?
So I believe it's the concentration rate for the mixture, or surfactant that of the ink alcohol mixture. Because the surfactant, the concentration is the reason why it causes a surface tension gradient. So when the alcohol mixture has a higher concentration, it causes a greater surface tension gradient, which causes the Meringen flow to be more to be larger, or the spreading speed will increase because of the greater of the surface tension gradient.
So you think it's the concentration, the most important factor?
Yes.
How about
I think the evaporation and concentration both contributes to the surface tension gradient. Yes.
okay. Any other question? No? Then okay.
So how do you think the dropping height or the speed of the droplet could impact the final number of fingers?
Okay. So when the dropping height is increased, let's say, it's going to create a greater dip, meaning that the surface tension, the rise level of surface tension is going to be lower. And it's going to dip more down into the plate. So it's going to have more time to come out of the plate that it created the dip. So it's going to travel less.
Can you turn to a gravitational force, gravitational point? So I believe that when having a higher dropping height, it causes the initial moderate droplet, I'll call it moderate droplet, like the first droplet that haven't spread yet. So it causes it to be spread more, like the radius will be more bigger. So it causes, so the initial moderate droplet will increase. So this part's radius will increase if the dropping height is larger. And however, if the height is larger, it might cause a greater impact for the capillary wave when it drops. It might cause like fluctuate this part and causes more random fingers to form.
Oh, the height of the drop. It's because of it has the gravity and the gravity force. Maybe it will change the radius of the inner circle from the beginning. At the yeah.
Okay.
So I have a question for the opponent review. So according to the reporter's conclusion, the second point, he was just said they did an experiment about a sexual rated evaporation, and those results will violate Stephen Taylor instability. So
Sorry, it will violate what?
can you go into your concluding remark? So you said their experiments disprove the Stephen-Taylor instability. So what's your comment about it?
I guess to use the instability, you would have to be ideal, but from the condition that you gave, you wouldn't be able to apply it.
It will be regarding like the viscosity from like small to the viscosity that's greater, so it causes instability inside the system because there's different velocity viscosity.
Okay. Okay, let's start here. And now we will ask the reviewer to give the floor. Ready? We start from reporter, right?
From the reporter.
Yeah, for the reporter. 8, 8, 8, 7, 8. Okay. For the opponent. 9, 7, 8, 8, 8. For the reviewer. 9, 8, 8, 7, 9. Okay, thank you. Now let's take a break. Okay, let's start this afternoon, the second round. The reporter will be all-nighter, and the opponent will be Sarah here, and the reviewer will be Anita. And the problem chosen is number 6. So please write down the answer on the whiteboard. The reporter has 5 minutes to prepare. Okay, time.
So, hello, I'm Charlene, and I'm presenting for all-nighters magnetic mechanical oscillator. So, here's a phenomenon demonstration. So the problem statement states, secure the lower ends of two identical leaf springs to a non-magnetic base and attach magnets to the upper ends such that they repel and are free to move. Investigate how the movement of the springs depend on relevant parameters. So the focuses are on restoring a magnetic force, disappearing beats, and external coupling. So observations and preliminary analysis. So we see that for tin and so we test tin and copper to investigate the different magnetic characteristics. And investigating material bending. So there are three approaches that could be possible. First could be Euler-Bernoulli's. So what Euler-Bernoulli is that it fulfills all but one condition, which is that deflection should be beneath 10 degrees. And so for larger deflections, we need to account for larger deflections, but we need to attract the change in area. So that is not very possible. And for a plate theory, it is more self-consistent, so more rigorous, and it involves 2D bending, which is unnecessary. Therefore, we use Euler-Bernoulli's because it fulfills all but one condition. So next, applying Euler-Bernoulli. When we apply a force, when there is a force exerted on the leaf spring deflects by a function of Wx. So here is Euler-Bernoulli's equation, where the moment is equal to x plus f equals xf. These are the boundary conditions at the end of the strip. And since we're only concerned about the ends of the strip over there, we plug L in, and we get that over here. And so we get that the f of reaction obeys Hooke's law. And so first experiment is looking for the restoring force constant. So we attach one end of the leaf spring to a horizontal surface, and we progressively adhere small widths to the end of the spring. We get a force restoring up and mg downward. And so deflection is seen over here. And so the dependent variable is deflection, and the parameters are the mass on the end, the distance, and the area moment, which includes the thickness. And so for continuing on, we use a calibrated tracker to determine positions with higher precision. We plotted graphs of restoring force and displacement for various parameters, and for this one it is when L equals 0.13 meters. Using Euler-Bernoulli's, we get a theoretical K value, which is this, and an experimental K value is this. And so there's a 46% error, and this is likely due to the imprecise thickness when we're measuring the very thin strip. And so these measurements propagate to a large error because when you're measuring something very thin, then there is a lot of error. And so that could be the reason. And so investigating magnetism, magnetic force. The force between two magnets depends on the shape, magnetization, orientation, and separation. So if we model our magnets as thin cylinders, then the theory shows that Fx equals this. But if we assume that the distance is much larger than the thickness of this cylindrical magnets, we get that it is approximately this. And so we get that F is inversely proportional to x to the fourth. And so finding magnetic force, the dependent variable is distance, parameters are mass and incline angle. Using Fg equals F magnetic, we get this expression over here. So we collected the data and created graphs of force versus distance. We fitted a function of form Fx equals A over x for b, and this is the result. And so what we get is an experimental value for A and B. And so analysis could be large errors not within the error bars, and it could be contribution of the second magnet in the setup as depicted here. And analysis 2. Here we take the combination of the restoring force and the magnetic force. So here's the magnetic force and the restoring force over here. So what is acting on the left strip is F net equals mx1 double dot, and for the right it is F net equals mx2 double dot. And so using the equations of motion on these coupled differential equations, we solve these differential equations numerically with Python. So we use these experimental constants, the function, and the initial conditions. So observations. We see that the theory incorrectly predicts the oscillations right of the original equilibrium as such. And so this is due to higher magnetic coupling and results in rapid energy transfer. And it also incorrectly predicts lower frequency, and this could be due to insufficient restoring force and results in rapid energy transfer and large amplitudes. So essentially, we experimentally verified these values over here, and changing these values, however, yielded no significant fit to our experimental data, so it didn't really work. So what happened was that the observations are that the two leaf springs share the same pair of frequencies, and the theoretical frequencies are lower than expected. So these are the theoreticals. And so we were wondering if, we were curious if they were to be modeled as a typical coupled oscillator and whether they behaved in the same motion. So we used eigenfrequencies to test for that. For consistency analysis, we used eigenfrequencies to get that the frequency equals 23.5, contrasting with the experimental determination. And so, as expected, even with experimental values of determined constants, we can't assume a square root proportionality between omega and k and in our earlier analysis. And so, thus, we can't model it as a typical coupled oscillator. And analysis 3, magnetic field direction. So, we track the magnetic field along the region of the magnet surrounding in the x, y, and z directions along an axis over here. So, how we did it was we took a magnetic field probe and then measured it across over here. And so essentially we get that the field is a function of angle. The horizontal field is a function of angle. And so magnetic theory continued. So since due to deflections, there would be a vertical component in the magnetic field. So not all of the magnetic field is directed straight to the other magnet. So essentially we get that we have to find the horizontal component over here. And since it requires dw dx, we get this value from Euler-Bernoulli's over here. And however, we have to note that the magnetic field isn't a single vector. It is an infinite set of field lines extending to infinity, so this is also sort of a simplification. And so magnetic theory continued. So we have to graph the magnetic field correction components. So essentially what's happening over here is that on the y-axis, it is the horizontal magnetic field directed to the other magnet. And as we increase the force, we realize that the horizontal magnetic field decreases more rapidly. Correcting for Fm. Fm is a function of itself, and using a substitution trick, we get that Fm equals this expression. However, when we solve for it, it doesn't work out. So we approach it using a more unrigorous correction, and that this is using only the first order of the correction. So we multiply the magnetic force by only the horizontal component. And so essentially what happens is that there's a closer fit in amplitude. However, the frequency deviation is still large, and there's a disappearance of beats. And so we see, as indicated by this FFT, that this peak disappears. So essentially, this shows that the magnetic field correction is insufficient to modify the theory. So as we showed earlier, if the magnetic forces decay more rapidly with distance, we expect the beat phenomenon to be less apparent, which makes sense. So predicted frequencies. So increasing the predicted frequency. So magnetic coupling accounting for that didn't really work to fit our theory. So we adjusted the effective mass or restoring constant. So what we did was we increased the restoring constant in our fit, and we got the reemergence of beats and that the frequencies match well. And so therefore, by changing k and n, the theoretical frequencies more accurately match the experimental. So therefore, the Euler-Bernoulli, this is because Euler-Bernoulli assumes small deflections, and as the leaf string bends more, k is not a constant. So external coupling. So there's an important phenomenon, a common phenomenon, that when you put two unsynchronized metronomes on a coupled surface, eventually they would all synchronize. So here is the first normal mode and the second normal mode. And so essentially in our phenomenon, the second normal mode dies out. So we now account for damping contribution as indicated by this term over here. And so here are our theoretical fits. And what we observe is that there's a prevailing first normal mode and that there's a consistent FFT with improved peaks as seen here. So the prevailing first normal mode is seen by the blue graph, which is the right leaf spring, and the orange graph, which is the left leaf spring. And so we see that the right one moves toward the left, and then the left one moves to the right. So that is showing prevailing first normal modes. And so damping analysis. There's no means to rigorously determine the damping constant alpha. We played around with the Python program until a good damping fit was found. And we observed that damping improves frequency match as we add FFTs. And so there's a consistent observation with a regular damped oscillator. And so additional experiments here, this is when this is coupled, when our phenomenon is on the same rod, so it's coupled. And the problem statement states that it's a non-magnetic phase. But what if they weren't attached to the same phase? So we also investigated it when they're not coupled. And so essentially what happens is that we separated the original rod into two distinct ones, and there is no normal mode decay as indicated. So for external coupling, there is one clearly distinguishable peak and many noisy frequencies. And for the lower frequency, then there's a non-externally coupled system. And so we observe a disappearance of the second normal mode, and the energy is lost due to rod vibration. And this explains frequency deviation. So our conclusion is that our leaf springs can be modeled as cantilever beams governed by the Euler-Bernoulli equation. Contrary to commonly accepted theory, our experiments demonstrate that the magnetic field between two disk magnets decay as a power function with a power around 1.75. As predicted, the Phi phenomenon disappears when the magnetic field is modified to reflect changing angles. Differences between theoretical and experimental graphs can be explained with the inextensibility of Euler-Bernoulli to large deflections and with external coupling. Thank you.
Okay. Question from opponent.
You measure the natural frequency of the spring.
The natural
Frequency of the spring. It means that there is no magnet and you just release it and you see the wave that it produces.
Yes.
Do you measure the elasticity of the spring?
We calculate the K constant.
Okay, can you show your materials that you use for the spring? Are they metal?
This is tin. This is copper.
Okay. Do you have any equation of motion that can accurately describe the motion of the spring?
The equation of motion.
Yes.
It says it accounts for damping, restoring force as well.
Do you have any equation of motion? Yes or no?
Yes.
And can accurately describe motion?
Yes.
Do you quantify magnetic force
Yes.
and magnetic potential energy?
Sorry.
Magnetic potential energy.
What?
Okay, next question. Do you consider air drag in your system?
No.
No. Okay. How do you track the motion of the spring?
We use tracker.
A tracker. Do you have the pattern of the position? The thorough wave of the position.
Sorry.
Complete wave of the position you track.
Oh, yes.
Okay. Can you page 41? Can you explain why there is a height difference between the rulers?
There isn't a height difference.
Okay, next question. Do you consider gravity in your theory?
No, it's irrelevant.
No gravity. Okay. Does the magnetic force is constant during the phenomenon?
Magnetic force.
Yes, between magnets.
No, as
Okay, did you calculate the moment of inertia of the ruler?
of the ruler.
Yes. No, the spring. Or
Answer.
Yes.
Opponent has 3 minutes for preparation. opponent take the floor.
Honorable juries and fellow competitors, I'm the opponent from Think Excel here. Today I'm going to oppose problem number 6, magnetic mechanical oscillator. Problem statement: secure the lower ends of two identical leaf springs to a non-magnetic base and attach magnets to the upper ends such that they repel and are free to move. Investigate how the movement of the springs depends on relevant parameters. And we'll mainly focus on why the springs will have coupling motion and how the oscillating frequency change in different parameters, and what condition makes the coupling motion most significant. These are the strong and weak points of the reporter. We believe that they have clear observation video and illustration so that we can understand how they demonstrate the experiments and how they get the experimental results. Also, they demonstrate the phenomenon of the various type of motion in their report. However, they lack of qualitative explanation so that we don't understand how do the two leaf springs actually affect one another. They explain the differences between the theory and their experimental results, and they keep modifying their theory. So we think this is a strong point. However, they didn't measure the air drag because since the opponents think that this is the main dissipative source in the system. So I will discuss it later. And they use they use tracker to track the motion of the spring. However, they lack of parameters and experimental analysis in their report. These are the points the opponent wants to discuss later. First is the phenomenological explanation about the coupling springs, because we believe that there must be some relationship between the springs. And about their theoretical model, we want to discuss about the magnetic force and the coupling system, since it is a specialized system that magnets affect one another. And for the analysis, we believe that they use fast Fourier's transform in their report too. So I'll investigate about how the frequency of the waves changes under different parameters, and the eventually stop time of the system, since that they didn't consider air drag dissipation in their calculation. So I wonder what is the main dissipative force in the system, and the decay in amplitude. So how does the dissipative system they have mentioned will affect the decay amplitude of their experiment? And there are many parameters to discuss, and to include the magnet, we want to consider the mass of it, because if its mass is bigger, it's harder to move it. And the magnetic field strength, we want to investigate how strong the magnetic field will affect the motion of the pendulum. For leaf spring, we believe that the material of the leaf spring will cause a lot of deviation, since they use metal in their experiments. So I'll discuss it later. And the length of the spring, the elasticity of the spring, the rotational inertia of the spring will also affect the motion of the leaf spring. About the initial condition, we want to investigate about how is it released. It is stabilized so that it can enhance the reproducibility of the experiment, and how different parameters will change the motion of the springs, including the distance between the springs and the deflection angle we give the spring. So I would like to skip to the next part.
Okay. Discussion.
First, for the reporter, do you believe that when magnets and when there's a metal and magnets, when the magnet gets closer to the metal, if we can imagine the metal is like a coil, so that when magnetic field affect the metal, do you know that there will be a repel force between the metal and magnets?
Definitely, due to eddy currents.
So is that the main dissipative system in your?
No, I don't believe it's the main dissipative thing. What is the main dissipative force? Is essentially due to the vibration of the rod.
Vibration of the rod. So you mean that there is only transformation of energy between the rod, so that the system will eventually work?
Sorry, can you clarify what you mean?
Because you mean that energy, the motion of one spring will affect the other, right?
Correct.
Correct.
It's a magnetic force.
Magnetic force. Okay. So the kinetic energy. Why does the kinetic energy in this system dissipate? How does it dissipate? in your explanation.
Okay. So due to the coupling motion, so essentially they're both attached on the same rod, right? So when the leaf springs are moving, for example, when they're in the second mode, they're oscillating like this, and so due to conservation of momentum.
Opponent believes that the kinetic energy mainly dissipate because of air drag. Because when the spring is moving in high speed, the air will resist the system from moving. And we believe that the reporter ignores these significant parameters in their calculation, so that the coupling motion is less significant.
So you believe that air resistance is the main damping factor?
Of course.
I believe that.
I'm the opponent.
Okay.
Sorry.
Sorry.
And you mentioned that the two leaf string are stacked on the same rod in your explanation just now.
Wait, sorry.
You set the two leaf spring on the same rod. You mentioned
Correct.
this.
Yes.
For this part, the opponent believes that it will cause resonance between the two leaf springs. So the opponent suggests that first, the material of the leaf spring should be changed into different materials so that the magnetic field will not affect the metal.
Could I clarify
Okay.
what I meant? So essentially, I think that when they're on the same rod, there is a coupling motion that is created, and so that is what causes.
Also, you mean that is calculated in your theory, right?
Right.
Okay, we accept this explanation. And next, I want to discuss about how different parameters will affect the motion, since with lack of parameters analysis in your report, we believe. First, since you draw the wave of the paragraph, you draw the graph using Python in your report, right? So this is fitting.
Which one are you talking about? Could you clarify this slide?
The Python, you show the Python results.
Is it this one?
No, I don't think so, but I think I can continue on this, continue my discussion. And that's because this a beat.
Okay, beat or not?
It's because when this is one of the motion of the spring. So when its amplitude gets higher, its kinetic energy gets higher too. But when it's slower, it transforms the kinetic energy to the other. You agree with this explanation?
I do.
Okay. And I want to discuss how different parameters will affect the motion of the waves. So if we secure the leaf like this. So which parameters do you think that will affect the pattern of the beat? For example, the distance between the coupled system or the length.
Correct. So as the distance between these two increase, the force between them decreases, and so that also decreases the coupling motion and thus decreases the beat.
So you believe that the distance is longer, the force is weaker too, so that it will make the beats longer?
Beat phenomenon does.
Oh, the opponent partially agree with this because when we take a look at the point of view of energy, it means that when the distance between these two springs are longer, it means that when this spring wants to transfer the kinetic energy to the other, it has to repeat more times to transform into the other. Okay. And how do you think the length of the spring will affect the parameters of the pattern of the wave?
So the length of.
Yes.
So like if you
Increase the length. So the opponent believes that there are many experiments done in the reporter's report, but they lack the simple qualitative explanation about the motion of the spring. And the opponent also believes that when the length of this leaf gets longer, the distance between these beats will become longer as well, because it will take more time to experience a vibrate. Okay. And how do you change the magnets in your experiments?
What do you mean by changing that?
Like the magnitude of the magnets affect the motion of the springs.
Magnitude of magnets. Well, we think that by changing the size of the magnet, it would affect the phenomenon.
So you say changing the size of the magnets, but not changing the magnetic force, the magnitude of magnetic force of the magnets.
Sorry, can you describe that? I'm not entirely sure what you're talking about.
So I'll say it again. So what if you change the different magnets in this system? How will it affect the motion of the spring?
If you change the magnet, so like, how do you change it? Do you, do you change it? You use like neodymium magnets.
Oh, you use a different magnet. No problem. I mean that when you change the amplitude, like stronger magnetic force.
Yeah, the strong magnetic force would
Oh, yeah, okay. Yes, please.
would increase the force of like the magnetic force between them
And about the pattern of the
couple
leaf.
and make beats more apparent.
Make the beats more apparent. I believe that the reporter's explanation is a little bit ambiguous because the opponent believes that when the magnitude of magnets gets stronger, it means that it tends to transfer more kinetic energy into the other one because the relation between the magnets are stronger, so that the beats will become, the distance between the waves will become shorter, which means the frequency will be higher. And can you show me that how you measure the, I think it's the elasticity of the spring. I saw you had fitting constant, right?
This?
Yes. Do you think that the deviation in this part will, what do you think that is, there is a deviation in this part? Because it seems that when it increases like 0.5 centimeters displacement, the data still look the same. Things like.
The data looks the same. So we're saying, the whole point of this is we're saying that there is a large error, and that is due to when we're trying to find I, which is the aerial moment, we have to measure the very, very thin strip, right? So if we have to measure something very, very thin, there would be a lot of error in the calculation, in the experimental.
Wait, since you mentioned that the spring is very, very thin, do you think that, and also you use a metal, do you think that when the experiments progress, it will bend because metal has the characteristic of easily being bent?
Being bent wouldn't affect it.
Oh, the opponents think that the materials should still be considered. And can you explain why you still use the data from this fitting constant, even if there are 46% of error?
You're
So
saying like why?
why is there such a big error and you still use the number that you got from the fitting constant?
I don't use the number I got from the constant. The whole point is just to see a sort of trend. It doesn't really matter as to the exact number. We're just looking at the trend that the law would
Okay, I agree with the explanation. And can you show the chart that you fit the magnetic force? Like you use the Gauss meter, right? You measure the magnetic flux density. And the result.
Okay, time is up.
Thank you.
Opponent is summarized in 1 minute.
Honorable juries and fellow competitors, this is the discussion summary from Think Excel here. Today I'm going to summary problem number 6. And we believe that the material of your setup should be improved as metal is the big problem because when it interacts with magnets, it will have repel force. And also, metal has the characteristic that it's easily to be bent, so that if the experiment progress, more deviation may be caused. Also, for the fitting part, we believe that there is a lot of deviation between the fitting line and the data they collected. So the opponents believe that they should increase the amount they fit. And also, we discussed the parameters of level effect. We believe that the length of the spring, the distance between the springs, and the magnitude of magnets, etc., will affect the motion of the springs and also the pattern of the waves. Thank you.
Okay, reviewer.
Do you think the oscillation is the simple harmonic motion?
Can you rephrase it?
The oscillation is the simple harmonic motion, yes or no?
We partially agree because you can simply describe it like that, but we believe that it's a more complicated system.
Okay, so do you think it's a kind of damping motion?
Of course.
And what causes the damping motion?
Air drag is the most significant parameter.
Okay, and how do you think
magnetic force is the most and also vibration.
and the simple harmonic motion?
A simple harmonic motion, it is simplification, but if you want to simplify it, you can.
Okay, and how do you did the system force you by did the force by hand or what?
By hand, and I make sure the initial condition is always the same.
Okay, and when the right oscillating velocity slow down the left pole, it will also slow down or oscillating faster.
I think it will oscillate faster because I introduced in that graph transforming kinetic energy from one beam to another.
Okay, and how do you think?
I agree.
Okay, and how do you think the energy transform here? Energy
So
transform.
how energy transformation works. So I think just like as you deflect the strip, the magnetic force interaction between them causes the energy transfer from one magnet to the other.
Okay, and how do you think?
The opponent believes that we can separate the energy into the kinetic energy and the potential energy. The kinetic energy include the velocity of the magnets and also the elasticity, the velocity of the spring should be considered. Potential part is the elasticity and the magnetic potential. Yes.
And are the two leaf spring have the regular movement?
So
Are the two leaf spring have the regular movement or not? Regular movement. Does it have?
yes.
Yes. And how do you think?
I can describe more because we believe that one of the amplitude is higher, the other will decrease. So we believe that there is a circular motion that will repeat the motion of like coupling.
And where does the resilience force come from? From magnetic force or the leaf spring?
I think it's the air drag from the leaf spring because the magnetic force only transfer kinetic energy to the other one.
Okay, and how do you think?
I believe it's due to the material of the leaf strip.
Okay. Thank you.
Okay. Reviewer has 2 minutes to prepare. Time's up. Rồi we will take the floor.
Hello everyone, my name is Usashi from Tin Emitter, and the topic of my report with my review today is problem number 6, magnetic mechanical oscillator. And here's the problem statement, and the main point is movement of the springs, and we are focused on how strongly do two magnets affect each other, and how the length of the poles affects vibration, and if the magnitude of the magnet affects the vibration. And here is overview of the reporter. They observed the two leaf springs first share some pair of frequency, and the theory is first analyzes convention and Euler, and German and damping couple oscillators, and the magnetic theory and the damping, and externally change the magnetic mass and force and field, and return force and external coupling, and and the process compare the theory and the experiment, and many graph on the experiment, and do many experiments to compare, and good time management. And they get the units on data graph and don't explain the phenomenon detail, and use too much formula and don't explain every formula clearly, and don't consider the air resistance, and don't measure magnetic potential energy. And here is overview of the opponents. The distance between the two springs is called the repellent force to. And the reporter didn't define. The process X next person to reporter, and the concepts don't let the reporters understand very well. And here is the discussion. The opponent asked when the kinetic energy disappear, and and our own opinion is energy. I think is when we pull out the pole, it will have kinetic energy to move, then it will have potential energy. Also, the magnetic will give a repulsion and air resistance to transform energy. And the opponent asked how you measure elasticity of spring and material should be considered. And the reporter said, and our own opinion. And when the right oscillating velocity slows down, the left ruler will also slow down or oscillating faster, and the opponent say faster. And our own opinion is it will become faster and then smaller, and another will be the same situation. And did you think it's related to damping motion? And the reporter said yes. And what caused the damping motion? The reporter said magnetic fields, and the opponent says the air resistance. And our own opinion is yes, but it's not the under damping motion. And the cause the damping motion is the air resistance. And did you think the oscillation of ruler is the simple harmonic motion? And the reporter and opponent also say yes. Both are say yes, and our own opinion is the damping motion here. And if there is only a ruler oscillating, and it will be a simple harmonic motion. And here is the missing point: don't discuss the experiment and don't discuss the effect of the air resistance. And thank you for your attention.
Okay, the reporter take the concluding remark.
Thank you for the opponent for a great discussion and the reviewer for thoughtful comments. So for a reporter's concluding remarks, we would like to say the qualitative explanation for damping is there's a superposition of two types of magnetic coupling, leaf springs moving together and moving against each other, and which leads to vibration, which causes damping the most, not air resistance. So the B phenomenon, as magnetic force increases, there's more coupling and therefore more apparent H phenomenon. And so changing the magnets, so we change the material of the spring, which is sufficient enough because we change the bending symmetry with the strength of the magnet. And so the bending of the strip is also negligible because our leaf spring is oscillating about the potential energy minimum. So Hooke's law applies. And so we have a logical and sufficient quantitative argument that the opponent did not discuss, which shows our fulfillment of the problem task. Yes, thank you.
Now, question from the jury. Question? Okay.
So I have a question for all of you. For example, when we're talking about electric potential energy, right, we think about it as two charge, and we bring together. So there's a Coulomb force between them, and you will have a potential energy, electric potential energy. And since all of your discussions, you're talking about magnetic potential energy. So what is the magnetic potential energy?
Like defining what is magnetic.
You don't need to define, but you just say something about. For example, I just give you an example. I talk about electric potential energy. So, what do you think about this magnetic potential energy?
You want to
Can I
start?
answer first?
Yes.
So the magnetic potential energy is the potential energy between magnets, of course. And this is the magnets. It means that we believe that there are potential energy. So when the magnet get close, the magnet will accelerate and stick on my fingers. And when the forces, the poles are opposites. It means that if there is no potential energy, if I drop the magnet, it will directly drop. But if there is potential energy, it means that it will have repel force for the magnet to fly out. So you can see that if I close the magnet, it intends to fly.
You don't need to say those phenomena. I just want to talk about a basic idea.
Oh, thank you.
Like the electric potential energy, you will know it's come from the Coulomb force. Right?
Right.
So you talk about the magnetic potential energy, you should expect something. So what do you expect?
Oh, we expect.
Like you talk about gravitational energy, right? You know there's a gravitation force. There's a gravity between two objects, so you have a gravitational potential. Now you talk about electric potential energy. There's a Coulomb force between these two charged particles. Now you're talking about a magnetic potential energy. So what's the potential energy? You are talking about.
So I believe that it's caused by the force between two magnets, and so the change in the magnetic field creates a difference, and then that causes the potential magnetic energy.
Because it will oscillate, so it will have the magnetic potential energy.
No question.
Okay. I have a question. How do you think about if you change the material of your spring? If the spring constant is larger, or then what do you think?
So I think when the spring constant is larger, it's stiffer, right? So the phenomenon would be less affected by the motion generated by the energy transfer from the deflected magnet, the deflected strip to the other strip.
You mean the damping will be smaller? The damping will be smaller, the damping motion.
Okay. So, damping motion.
Yeah, actually, your vibration will die out, right? Eventually.
Yeah, the vibration.
Yeah. So, okay.
So the amplitude would decrease.
How about you change?
Oh, so when you change the material of the spring, it means that when you give it a force, the displacement of the material will be different. So we can hypothesize that we are just extending the length of the spring. If it's shorter, if you give it a force, its displacement will be shorter. And if it's longer, you give it a force, its displacement will be bigger. So when the material of the spring is changed, it means that the elasticity, we can hypothesize that the elasticity will change, and if it's longer, it means that they are more easily to affect one another, because a force given can affect more.
Okay. You want one answer?
The different material will have different elasticity, so it will change the force for spring, and maybe it will have different amplitude.
Okay. Time's up.
Thank you.
Thank you.
Now, ready? You will do the floor for the reporter. Okay, 8, 8, 9, 7, 8. For the opponent, 7, 7, 7, 7, 7.
Thank you.
For the reviewer, 6, 7, 6, 5, 7. Okay. Now we take a break. Okay, let's start the stage 3. And the final stage of this afternoon. Please write the name on the whiteboard. Your reporter will be Excel field. Opponent will emitter, and reviewer all-nighter. The reporter has 5 minutes. Okay, the problem will be number 4, the card of 9. Okay. Okay, the report make the presentation.
Honorable juries and fellow competitors, I'm the reporter from Typt here. Today I'm going to report problem number 4, color blind. Problem statement: when the compact disc, or DVD is illuminated with light coming from a filament lamp in such a way that only rays with large angles of incidence are selected, a clear green line can be observed. The color varies upon slightly changing the angle of the disc. Explain and investigate this phenomenon, and we'll mainly focus on why only specific colors were selected, why the colors vary by slightly turning the disc, and what is the composition of that light. This is the outline of my report. In observation, we'll show the clear green line that the problem statement mentioned, and how the color change when we increase the tilting angle of the disc. Explanation part will have quantitative information about why the green light occurs in this phenomenon and the light path difference. Analysis of color change. We change the tilting angle of the disc, the viewing angle of the observer, and laser calibration to verify our data. And we have comparison between CD and DVD. Finally, the conclusion. Observation. First, I'm going to introduce my setup. We use the filament lamps that the problem statement mentioned to use as our light source, and the camera as observer. We make sure that the distance between the DVD and the camera is 1.5 meters far, so that we can ignore the deviation caused by the tilting angle. And we make sure that they are in the same height to make sure that they are in the same horizontal surface. And for the tilting angle of the disc, we use the Arduino to control the motor to control the tilting angle of the CD to make sure that there is no deviations. Okay, for an analysis of the color part, we use CIE chromaticity diagram to analyze the color we've gotten from the picture we got. And we obtain the RGB value of the color from the camera. It can tell us the RGB value. Then we can compare it to a CIE chromaticity diagram to get the dominant wavelength of the light. For example, at here, it is a green line shown here. So if we find the position of in the coordinate, and we from the center of this paragraph, from the center of this graph, and we have a line to connect it together, and the contacting point at here is the dominant wavelength of this light. And we have to know that there is no, you can't get a wavelength of light if the contacting point connects at here, and this will be explained later. Stage 1, when we tilt the compact disc in a small angle, we can see that there is obvious green line in the diameter of the disc. However, if we increase the tilting angle of the disc, we can find that the color varies, and multiple green lines can be seen during the if we increase the tilting angle. Explanation. First, I'm going to explain why there is a green line on the disc. First, we have to look at the micro scale of the CD. We can see that there are small ticks on the CD, and we call this pitch. Yes, the distance between this is a pitch. And we measure that the pitch between the CD is 1.6 micrometer. And then we have to calculate the dominant wavelengths that were gotten in our experiment. When the light comes from the light source, it will reflect back, since the tracks will reflect the light. And we can see that when the distance between these tracks, you will have distance for distance. And if this distance is equals to the wavelength of the light, we can get the wavelength of the light by calculation. Also, the distance between these contains two waves too, and three waves as well. So we can get many kind of wavelengths in this constructive interference condition. However, there are some boundary conditions. That is because that human eye can only see the range from about 400 nanometers to 700 nanometers. So the only light we'll see when the tilting angle is 50 degrees is this. And what is this? This is the green light. Because the green light, as the wavelength is about 500 to 600 nanometers. When we start to increase the tilting angle of the disc, the color of the light will be changed. This is because the linear distance between these pitches decrease, so that we can find that the original length is 527 nanometers. It will decrease into 483 nanometers. We can find that the tilting angle increase, the wavelength will decrease. Then we have to calculate the relation between the tilting angle and the dominant wavelength. We can first find the linear distance between these tracks as the distance between the track times the cosine value of the tilting angle. And then the observer angle also affects the experimental results, as the light source, when the light source arrives at the disk, it will reflect from the tracks, and we can consider that on the track there is a new light source, and it will reflect the light back to the observer. And for the distance this light walks and the distance this light walks, there's a difference between this distance, and we calculate it through the cosine value. Next, we analyze the tilting angle of the tilting angle, how tilting angle will affect the experimental results. We can find out that the wavelength actually increased instead of decreased, and there are negative wavelengths. I will explain this later. And also, there are unexpected wavelengths that doesn't appear in our theory. The negative wavelengths. And I'll explain negative wavelengths because I mentioned that if the line is connected here and the contact point is here, it doesn't have a wavelength. This is because that the diagram can only analyze monochromatic light. It means that light only compose one wavelength. If there are multiple wavelengths multiplied together, it will arrive at here, and the data will be error. The algorithm to calculate the wavelength, so it will be negative. From this result, we can find out that the lights coming from the disk actually compose different wavelengths, not just one wavelength. And for the negative wavelength part, we use a prism to separate the lights coming from the disk, so that we can know that what are the actually lights that compose the purple light. So we can see that originally this is the purple light, and we adapted a prism, the light will be separated. And when the tilting angle increases, we can see that the light is separated by the prism. Next is about the unexpected wavelengths. We found that between one tracks there can be constructive interference. However, between two tracks there can be constructive interference too, and the wavelengths will be multiplied by the track they crossed. And we have to notice that the intensity also changes too. Because for if we only consider the cross one track, the wavelength of lights can form constructive interference every one track. But if we consider it across two tracks, the lights can compose every two tracks, so the intensity will be inversely proportional. So we only consider when the tracks cross 1 or 2, because the intensity will be stronger. So this is the experimental result when we use prism. We can see that the tendency of the data begin to fit our theory, because when the tilting angle increased, the wavelength began to decrease, but there are still a little deviation. This is the result we got from rotating angle B. We can see that there is a horizontal tendency that the wavelength of light will form. Also, when we change the alpha angle, there is a tendency of horizontal line will be formed. So I'm going to explain this phenomenon. It seems that the camera is more sensitive to specific wavelengths. Like if it receives dark blue, it will change it into blue, and if we receive light blue, it will change it into blue too. So it will have a tendency to make the wavelengths into the same amount. To avoid this, we have to have another calculation. We use a laser to shine on the disk, and we found out that we project two kinds of laser on the disk and find out that there will be two lines. Because the refraction of the prism, the coefficient will be different, so that the position of the light changed by the prism will be different as well. And we can use this equation to get the actually wavelengths of the light by mathematical calculation. After the calibration from laser, we can see that originally the wavelength of light will be affected by the camera. However, when we use mathematical calculation, we can find out that the wavelength started to fit our theory. This is the small conclusion. Initially, there is a green light, but it is composed of two different lights. Through our prism, we can tell that. And when its angle is about 20 degrees, it actually composed of three lights. But when we analyze the intensity of the light, we can find out that during the green light section, the intensity will be stronger. And for the negative part, we believe that the prism can fix the problem. Then we compare CD and DVD. We can find out that the pitch between the DVD is smaller. So that if there is a pitch distance difference, we can find out that the DVD cannot contain that much wavelengths. Originally, the CD can contain 1, 2, or 3, but now the DVD cannot contain only 1 or 2. So the theory line will be smaller. Why do we see a green light? This is because the constructive interference between the tracks. How do we analyze the experiment? Originally, we used the color CIE graph, and then we used the laser calibration to adapt our experimental results.
Okay, time is up.
Thank you.
Question from the opponent.
So for the first question, I want to ask you, how did you define the green light in your experiment? If you use the neck eye or use the machine here?
What do you mean neck eye?
Neck eye. You use your eyes to see the light, and you define the green here, or you use the machine to define it?
Oh, our eyes can see the green lights, and our camera can also picture the green light as well.
Thank you. And another question is, do you think the light only appear at a large angle or?
For the stage I mentioned that when the tilting angle is small, there will be green light, and when tilting angle is bigger, the light will change, but green light will also appear again.
Okay. So do you have the range of it?
The range of it. Like here, we can see that 600 and 500, so about smaller than 30 degrees, it will be green light.
Okay, thank you. And another question is, do you analyze the composition of the disc?
The composition of the disc. Yes, we use a microscope to see that there are actually small tracks on the CD.
Okay. So when the stroke of the CD is increased, the power of the green light will also increase. When the stroke of the CD increase and the power of the green light will also increase too.
Power of the green light. What do you mean with power?
That the green light will appear more appear.
Can you rephrase it all again?
Just when the slit of the CD is increased, and you can see the obvious green light here.
Oh, you mean the slit increase? That means that it can contain more wavelength. So I cannot sure that the composition result will be green.
Okay, thank you. And do you think the power of the light source is a major in this experiment?
Yes, because it is a
Time is up.
spectrum.
Thank you.
Opponent has 3 minutes for preparation. 个关闭投影机，来重新开。Okay, the opponent take the floor.
Hello everyone, I'm the opponent Yezichi in Team Emitter for number 4 color line. And here is our problem statement, and we are focused on the compact disc or DVD, and for the finger length of the large source, and the large angles of incidence, and the clear green line, and the angle of the disc here. And our main focus first is what we can observe along here, and the range of the green line's angle, and how the color change from turning the disc. And here is overview the report. So we can see in the green line, it will appear on the disc, and when it is at the small angle, it will appear to the green line, and when you turn to the big angle, it will also in the green line. And the color will change from turning the disc. And for the third row, they change the CD analysis from the tilting angle and the negative wavelength and the unexpected wavelength and the depression grating here. And for the experiment, they use the different disc to compare with the CD and the DVD, and also they use the laser calibration and change the angle of the disc here. And for their conclusion, the green line can be seen with the large incidence angle, and the green line caused by the grating, and the line is the maximum of it. And for his advantage and for the report advantage and the suggestions, and we think he has the clear data in his report, and also detail explain the zero and have the clear explain of the experiments. And for the suggestions, I think he needs to mark the place clearly of the light in the experiment picture. And I think he needs to explain the formula more. And I think he needs to have the more parameters here, like maybe he can compose the maybe he can change the observed place here. And for the points to be discussed. And for third row, we will discuss for the CD analysis from the tilting angle and the negative wavelength and the differential grating and the unexplained wavelength here. And for the experiment, we will discuss for the use different disc and the CD to compare with the DVD and the laser calibration and change the angle of the disc. And thank you for your attention. And I want to discuss for the report now.
Okay.
say you analyze the color for the spectrum from the light source, right?
Exactly.
Exactly. So, and so, what do you, so in the light source, how color relative strength is more stronger?
You mean the intensity?
Yes.
Turn to page 22. 25. The intensity will change like this. It means that the camera itself will be more sensitive to green light. So the result of the intensity will result like this. The green light here is more stronger.
Okay, so because you think the light source is the important thing in your experiment, right?
The light source, we believe that it should be a continuous spectrum.
Spectrum, okay. And so if you change the light source here, and it will have the different color for the spectrum, right?
Change the color here.
Yes, light source. Change the light source here.
Oh, you mean the viewing angle?
Light source.
Light source. Oh,
The
the angle of
illuminated angle.
the angle of the position of the
CD.
position of the light source. Yes, it will affect the experimental results.
Okay, and can you go to the page 14? So I think here's the diffraction grating. Yes.
Diffraction grating.
Yes, because you put here is the dark and the bright and the dark and the bright, and I think it is diffraction grating.
The picture is to represent that this is the track. This is the track, and this is the distance between the pitches, and the light will reflect.
Yes, but can you explain the 0, why it will have the dark and the bright and the dark and the bright? Because I think it maybe have the constructive and the destroying the.
Oh, this is just an illustration that symbolize the structure of the CD. And if you want to analyze the constructive part, into page this part is when the lights come from the light source will reflect back. And if this distance, the linear distance, is equals to wavelength times an integer, and it will form constructive interference.
Okay. And can you go to the experiment video?
Experimental video. Fine.
Because I can see in your experiment video you change the light here, and when you change it, it has the curve. And what do you think it will have the curve?
The curve would mean that the light isn't always straight.
Yes, do you think the light is always straight?
Yes, it only forms in the diameter of the CD.
But when you move it, it will have the curve, right?
A curve, I mean the CD will curve.
When you change the angle of the CD, you can play the video and you will see the curve right here.
Where?
For another video.
For another video. 18. Wait, my computer is lagging. Oh, you need this?
Yes.
Oh, this is the result of the prism because it separates the different wavelengths of light. So we can analyze the composition of the dominant wavelength.
So do you think the light when it's illuminated the disk and the ring color will observe, and do you think it's a line or is it dot?
A line or a dot. Can you rephrase again?
Because when you illuminate it and the light will separate it, right?
Yes.
So do you think it will, why it is only have a line and not a, because the light will.
Oh, so you mean the position of the light only exists here in the diameter? Oh, can I use the blackboard?
Yes, please.
Suppose that is the CD, and there are small tracks on the CD. And we can find that the
Stage is different.
the direction of the ticks, of the little ticks is perpendicular to the lead like this. So only in this situation, the light from light source can reflect back. Otherwise, the light from other source will reflect to other angles. Only the diameter will have the light.
So don't you think it will have this or this?
I think we should not consider the of the
This is of the CD?
yeah.
Okay, so do you use the same CD into all the experiments?
Of course, and we also compare it to a DVD.
Compare with the CD, and you also tell me in your short question, you think you analyze the CD of the compost.
Can you rephrase?
You analyze the CD of the compost that the CD have some layer, or you analyze the CD. So your question with that?
Do you use a microscope?
Yes.
Oh, we have actually go to the laboratory and look at the structure of the CD and see that there are actually little ticks on the CD, like this, the little ticks.
So you don't compost the CD. What is compost by?
Only the structure, the layers of the CD, backup. So, Yes. We believe that the shiny layer here will reflect the laser back, and there are little ticks on the CD, so that this it will change the direction of the reflection.
So here's the plastic on the CD. I think it will have the 3 layers.
Yes, there are layers on the CD. We mainly focus on the reflection, not the structure of the CD.
Because I think the plastic on the plastic on the CD, maybe it will influence when you image the light here, maybe the plastic of the stick will influence the experiment result.
Maybe we should consider the diffraction rate coefficient of the.
Maybe it will reflection the light here and it will have some light into the strip here, but I think maybe it will emit when the light emitted and it will have some reflection too.
Okay, we agree with this part, but
So do you remove the plastic on the CD?
Yes, I believe we remove the CD upper part. You can look at it. Thank you.
So the CD and the DVD sticks will have the difference, right?
Yes, because the pitches, the length of pitches is different.
So the DVD and the CD will also have the same difference, right?
We ignore the thickness.
You ignore the thickness, okay. So can you go back to the experiment data? Page 18, please.
Or which data do you indicate to?
So you just say when the light angle, when it is small and it turns to big, it always has the green light.
Green light? Only the small angle. Both of green light.
So you think it only has the green light only appear in a small angle?
No, when the angle increase, the color will vary, but green light still appear several times.
So what do you think the red light will appear here? Do you think is the wavelength of the red light very big, so it will appear in this?
No, in this section we discuss about the originally it is purple light, but if we use a prism to separate the light into different wavelengths, we can find out that it is composed actually by blue light and red light. So it doesn't contain green light in this part.
So the laser, so do you analyze the laser?
Analyze the wavelengths of the laser.
Spectrum.
Spectrum.
Yeah.
Do you mean
Because the laser illustration, because in a different laser it will have the different spectrum, like the blue color will have the more intensity, or or the green color will have the more intensity?
The laser we use is only to calculate the wavelength, so its intensity doesn't matter that much. And for wavelength part, we assume that it only contains one wavelength, so we can use the data directly.
Okay. So, so why do you choose the laser here or not different light source lights?
No, we use the number of the lasers doesn't affect that much because we can still use this equation to calculate the actually wavelengths through this equation. As we mentioned, the distance between the line we want to measure and the red laser we adapted and the blue laser we adapted.
So for the CD and the DVD, can you talk to the CD and the DVD computer? Here. So you say you use the microphone to hear, so if the CD is
Okay, time is up.
okay, then
Opponent has 1 minute to summarize the discussion.
so from the discussion we discussed about the layer of the CD and you can find the report we say we have I think the CD will have the 3 layers here and the move one is the plastic and another will have and number 2 layer will have the stick and move. And in the report it has the 4 layer here and one it will have go from the line not the dot or plane because when the light illuminated and you can see the line here and we think the reporter's picture will change the light source and reporter don't explain it clearly and I think it will affect the results because when you change the angle it may have it will appear the red light here and okay, so thank you for your attention.
Okay, question from review.
Can you go to your experimental setting?
Page 5.
Okay, well, it's okay. Yeah. All right. Can you? Yeah. For that one, did you make sure that from your filament lamp only do you use a slit or some light blocking mechanism so that you can only get one angle of light to go through to the disc?
To go through to the disc. Even if the lights go into different direction, it won't affect the experimental results.
Okay. Can you go to slide 10? Slide 10. How did you measure the grading distance? Because it's in micrometers.
Oh, we got the reference of the distance.
Okay. Can you go to slide 17? All right. Can you elaborate on the units of your chromaticity graph of the XML?
I think it's 30. Oh, this is just an algorithm we use to calculate the wavelength of the light. How it works is complicated. Yeah.
Okay. And then do you agree that there is a plastic film on the CD or DVD surface?
Positive film on the CD.
Plastic film.
Oh, you mean the opponent just mentioned?
Yeah. So do you agree that there is a plastic film on the
Yes.
DVD? And if so, do you think that it's because of it, it will change the index of refraction? Because
Maybe it will have some reflection, but reflection of the light you can see is not the major issue.
And how did you measure the color intensity of your experimentally observed green color?
Oh, the camera can
For
tell
example,
you.
like the red intensity. You can go to the graph where you show the intensities.
Like this?
Yeah, how did you measure the relative brightness and intensity?
Oh, the camera can tell me the results.
And then for a CD, the grading on the CD is in a curved shape, not a uniformly parallel like a normal diffraction grading. So how did you account for that in your measurements?
Actually, compared to the size of the CD, the track is really small, so we can ignore the curved shape of the track. Yes.
Okay. Do you think that the curvature of the grating will affect the phenomenon?
Temperature?
as in like it is not all the grating is not parallel, but rather the whole thing is curving. Okay. And do you think that changing the lamp color will affect the phenomenon?
The lamp color, like if
Let's say yellow or
single wavelength. Oh, with single wavelength, it will just reflect the single wavelength.
Okay, time is up. You have 2 minutes to prepare. Okay, do you take the ball?
Hi, I'm Justin and the reviewer for number 4, colored lines. Alright, this is my review of the report. They had a clear phenomenon demonstration and they also had a clear experimental setup. They also considered the diffraction order M, which was good, and they also tested some parameters, for example, like the tilting angle, which is the angle of incidence, and also the disc type, for example, the CD or DVD. And then they also had a good use of the prism to distinguish their colors. They also had a clear qualitative explanation for the appearance of the green light. However, as for some improvements, they didn't consider about the CD's grading curve. There was also a lack of a theory or a quantitative explanation for theory lines, for example, when they're comparing between the tilting angle and the wavelength. At the same time, they also have unclear graph axes for the chromaticity graphs, and then they did not clarify if the report, if the report actually used slits or to ensure that light from only one angle hits the disc. And then they also did not consider about the CD or DVD's surface plastic film, and then their explanation for how the green light is measured is also kind of ambiguous. And then they also tested too few parameters because their data for the parameters are too few because they only included 2 DVD or DV types. And then they also did not measure, the measurement was inaccurate for the intensity. Okay, and then this is my review of the opposition. They had a good overview of the reported presentation and asked many relevant questions, such as the thickness of this, the plastic film, but at the same time they also asked some irrelevant questions, such as the distance between the CD holes, and then there was somewhat of an unclear communication between the two. Going on to key discussion, they first talked about the curvature of light, and the opponent asked that, why is there a curvature of light when this is turning around, the angle turning? And then the reporter said the light is always straight. However, we disagree with the reporter because when there's a curvature of light because the overall grading structure in the disc, it curves around and is not always uniformly parallel. Alright, and then they also discuss about the structure of the CD. And the opponent suggests that there exists a plastic on the CD which can influence the illumination of light. We agree with that because the plastic film will affect the index of refraction. The opponent also asked about the thickness of the CD, and the reporter ignored about it. I think it's important because the angle of incidence will be further affected due to the index of refraction of the surface material. And then going on to our questions, we asked about the need to use slits to ensure one angle hits the disc. The reporter says no, but we think it's important. And then I also asked about the intensity of the light, and suggested, and then they said, well, the camera can tell the results, but we think that they need more sophisticated mechanism to tell that. And then curvature is also an important factor that the reporter did not consider about. And some of the points missed are that they didn't really consider about the plastic film thickness on the CD surface, which will influence the index of refraction when the light hits. And then their intensity measurement for the green color is also somewhat ambiguous and inaccurate. And at the same time, they also did not consider about the CDs and DVDs curved grating structure, which is different from a normal grating, diffraction grating.
Okay, thanks, Rob. The report of concluding remark.
This is the concluding remark from the reporter. As the opponent and reviewer mentioned, they mentioned that the curve of the CD and the thickness of the CD will affect the experimental results. And we believe that the thickness is so small that the little curve doesn't really affect the big deviation in our experiments. And the probability statement mentioned that we should focus on the phenomenon, how the phenomenon occurred, is not how the structure of the CD occurred. And for the CIE axis, the chromaticity diagram I just mentioned, the calculation of that algorithm is so complicated that we don't need to focus on how we get the dominant wavelengths. For the theory line, we believe that we have shown that the wave path difference is equals to the distance between paths times cosine alpha, cosine beta divided by an integer. So that's this is the formation of the theory line. By using the calibration, we are able to reduce the original deviation caused by the camera because we can use the calculation algorithm. Next, the definition of screen light ranging from 500 to 600 nanometers, and we believe that both the camera and human's eye are more sensitive to this wavelength, so that we can observe the phenomenon more clearly. Though changing the observer angle better, we are still able to preserve straight lights. The curved lights the reporter had misunderstood might be caused by the prism that we are using to separate light. And the thin layer of membrane on the disk will actually not cause the big deviation in the results. However, we still reduce the membrane for this part of testing. The thickness of the disk in our experiment and theory line can be ignored because we only measure the composition of light in the middle part of the CD. And this is my concluding remark. Thank you.
Okay. Now it's time for you to ask questions. Any questions?
So I have a question for all of you. Opponent and reviewer, they emphasize the curvature grating. So now let's assume now you have the disk, right? You already have the curvature grating. So you see this green line. If you don't have this curvature grating, what would you see?
As you can see from their chromaticity graph, it was various angle, it was various position. If it was just a uniform, like normal grating, like parallel grating, then you will see the color spectrum like that, instead of at different spots in the XY coordinates.
I think it will have the rainbow colors like the rainbow and the color menu color on it, but it doesn't have the correct rating here.
In the theory part, we already considered that there's no curvature on the text. So the theory line we drew out comparing to our experimental results can wrongly predict the wavelength of light.
So what do you see? I mean, what do you see?
What can we see?
Yeah.
I can just tell because there are many different lines, and a tilting angle will have many will have the result of many lines composition together. So I can tell you which wavelengths directly.
Okay, the problem statement asks you to observe the range of the angle, incident angle, when the green line appear. Why don't you do that? Can you do that? Have you done that?
You mean
The range or the angle, the incident angle, that quantitatively can you determine the range of the incident angle?
we believe that this is the dominant wavelength, and between the 600 and 500, the data points between these parts is the angle that will occur green light. Like this part is above 600, so the angle directed at here will not appear the green light.
Okay. I don't have any questions.
So, the opponent and the reviewer mentioned the thickness of the film, the plastic film. So, what if we have a very thick plastic? How will be our result?
Yeah, since the plastic surface, its index of refraction is different from, let's say, airs, and then like light travels through air and then through the plastic into the grating. As you have a thicker amount of the plastic film, then your the angle will differ because the index of refraction, and then the amount, angle, distance, position will change because relative to how much distance you add to the plastic film.
I think when the thickness is increased, maybe the diffraction grating will have the same but different length. Maybe it can be cured.
We believe that the diffraction of the light will separate the composition of the light, so its function is just like a prism. So we can, we'll see more lights from our observation.
First for the question for the reporter. What's the width of your observed line? Do they vary? The width of your observed line.
You mean the width of the wavelength or the width of the CD track?
Of the line.
Of the lights.
You see different, at different angles, you see different lines. Do the line width change or you do not observe this?
We believe that the light from the lamp is a continuous spectrum, so it contains different wavelengths of light.
Yes, but you observe blue lines or red lines. Do the width vary? Do they have a width? You see in the continuous spectrum, your width is not the same. So
Did you use the
observe
slit?
that.
Did you use the slit to confine your width of light?
You mean the width of the green light?
Instant light.
Green line,
We believe that the angle, the tangent of the radius, if the take care can reflect the light back, the diameter of the light can be observed and measured. But we didn't calculate it because we expect how green light occurred.
Okay, let's stop here. And now the jury will be the score. For the reporter, nine 8, 9.
Thank you.
And for the opponent, 6, 8, 6, 5, 8. For a reviewer, 8, 8, 8, 8, 8. Okay. Thank you everybody.